important element, and the way time is treated within the model and the way that feeds into radiation varies between models as well as to how that's parameterized. So there is a bit of variability such that the extremes meet up again, but the way we get there changes in between. And as seasonality becomes an important element, seasonality is a real problem for projection, but that's what's changing, like we've got now. Like, shifting of the early spring is earlier, or, river ice, it breaks up earlier, especially at higher latitudes. Sea ice changes. The seasonality element is an important one rather than just a mean global annual. And also, some models over time tend to trend away from each other depending on what priority they get to different elements. So we might have two models that, for here, broadly speaking, are telling the same story, but as they go through over time, over 100 years, 60 to 100 years, diverge more and more, and you get the greater variability. So, we might say if both of these are acceptable over the 10-year time scale, over 2100, but let's forget about it and not worry about it at all. So how do we know that models work? This is the most crucial diagram you will ever see. It's the most important graph in the IPCC, full stop, without any question. If you don't believe in the efficacy of models and the probability of climate being affected, then this graph and an associated graph should suggest it. This is observed temperatures from 1900 to 2010. Running through it is the predicted or retrodicted temperatures using models. The model, the sort of basic ensemble model prediction of what temperatures should have been. And basically, therefore, the red and the black line is the actual observations, the red line is the model. And what you can see is that, okay, they're slightly different. This is smooth, and there's an error term on here. But what you can see is that the model is able to reconstruct global temperature over the last 100 years. So it must be doing something right. The second graph that I've forgotten to put in on this is that if you run the model without greenhouse gas forcing, so if you run the model but effectively say there's no greenhouse gas forcing, what happens is that from about here, the red line goes like that, and the black line, the observations continue to go. And I can't remember exactly the page that it's on in chapter 8, but you will find that in chapter 8, a key element of that, this is testing the model. This is testing the models against observations. I don't know where it is, there's so many in here. But effectively this is saying, the modelling works. We can reconstruct 20th century temperature using the model, just as a physical model. Therefore, why, if we can reconstruct the 20th century, can we not project into the 21st century? Okay, we have to make assumptions about how much greenhouse gas we put into it, but we've got a range. So whichever projection you use, we can assume that it's a reasonable estimate of reality, of what the reality will be. And so this is how models are effectively tested. They're tested against observations. They're retrodicted, if possible, or as time goes on, they're tested against what has actually happened. We go back to 1990, early 90s for the IPCC, middle of the 80s and the first modelling, and you can therefore say, right, over those 30 years, what's happened? Well, it's broadly followed the model and this particular scenario. And of course, the availability for the data that we use there is sort of going back about 100 years. We know we've got observations for about, instrumental observations for about 150 years at best, satellite data since the 80s. So we do have a decent global data set to actually work on. But it's now that we need, therefore, to be able to go back in time to look at proxy records of climate, because we do know that climate variation occurs on longer timescales than 100 or tens of years. And so the important thing is to be able to put that longer timescale in some context, and also to use it to try and evaluate our projections. And there are various projects. This should be COH, not CHO. I don't know why I left that in, but I changed it. There have been projects to try and produce data sets of certain periods in the past so that you can then run a model for, say, 6,000 years ago and run it against what the observations were and see if it seems to work. And you're testing the model again. This paleoclimate modelling is a comparison project, or the COMAP, the Cooperative Policy Mapping Project. So what we need to do is find timescales or time periods which are useful to the modelling process. And this is what Gavin Schmidt talks about in his paper as well. So I don't need to go into the paper, but the paper will emphasise this. LGM. When was the LGM? What was the LGM? Aspirational maximum. That's not a concern. When was it?
A while back.
A while back. Oh, okay, well, I tried the first year this morning. They looked at me, gone out. I actually raised it with them last week. They always look gone out anyway. Last glacial maximum, 25,000 years ago. Why is it useful? It's useful because it's the last period with huge variations in global mean temperature, because we've had the bloody great ice sheets everywhere. But it was stable, relatively stable. We had a period when we had these huge ice sheets close to their maximum in equilibrium. Therefore, we had a global climate which was very, very different from our own climate, but which was stable, more stable than any time since then until the Holocene. What that allows you to do is test climate sensitivity, and especially change to the carbon cycle. What drives climate change? Does climate drive the carbon cycle, or does the carbon cycle drive climate? Big question of what came first, CO2 or temperature. What drives what? Your climate skeptics say that CO2 drives climate, yes, but they will say that temperature in fact drives CO2. So in fact, CO2 is not causing climate change. It is climate change that is driving CO2 values up, if the two are linked. So what you can do with this is you can say, right, this is our cold world, stable world. Let's just tweak this. Let's tweak global patterns of ocean currents or something, a transfer of heat from the southern hemisphere to the northern hemisphere. What happens? Let's deforest this area, or let's begin to forest this area through normal patterns. What happens to the carbon cycle? What therefore happens? We just change a little bit and we see what happens. How does that stable state change? So the LGM is a useful slot for modelling, and you'll see models that are used for the future also used for the past. Last millennium, this is crucial because it's obviously the most similar climate we've got to today, with virtually very little, if any, anthropogenic forcing. So it's as near the natural system atmospherically as we can. Solar output, land use change effects is a big problem, but solar output and volcanicity, let's predict climate back. So in other words, what we do is with that graph, instead of stopping at 1800, we take it back to 1000 to 1000 and see what climate we get without greenhouse gas forcing. The 8.2 event is a really useful event. This was the last and only major abrupt climate change in the Holocene. It was a short, very cold snap, especially in the North Atlantic and Northwest Europe. It is probably caused by a glacial output flood from the Laurentide ice sheet that went out, lifted the Laurentide ice sheet, water came under it, into Hudson's Bay, all around northern Canada, flowed out into the North Atlantic, freshened the water, cooled the water. It led to a short, rapid cooling of the North Atlantic, limited the thermohaline circulation, and by doing that you can run the model and see how does what is predicted happened compared to what actually happened. It's quite fun because effectively what you do is what's known as a hosing experiment. So it's the equivalent of standing off the edge of Labrador with a big hose of cold, fresh water. You say, well, how much shall we put in? How many spur drops shall we put in? How cold will it be? And you just sort of choose your parameter of, an extra 2 million two spur drops coming in over 10 years at a fresh water at a temperature of 3 degrees. Pour that out into your model of the Atlantic and see what happens. And effectively, it's a very useful way of testing models to see, well, what does happen? How does it feed through? And does it lead to the same temperature difference on mainland Europe as we observed during the 8.2? And it gives an idea of models and notions, which is always useful. Pliocene, about 3 million years ago, again, relatively stable but much warmer temperatures. This tends to be looking at analogues and saying, if we had a world which was 4 or 5 degrees warmer, what's the world look like? This was our last stable, warm world. What does the overall was the temperature, the climate, the nature of the surface, the nature of vegetation, the nature of the carbon cycle, and what will it be? We do it by an analogue, therefore, rather than sort of running a model through a particular event. Oh, that's got a bit quicker than I thought. It's too hot anyway. So effectively, the whole modelling thing is that we've now got AOGCMs which are used as the basis for informing policy about things that could lead to changes in climate. We do, however, the science relies heavily on scenarios. The same models will give you very different outputs if you change the scenario of what you expect the model to do. And there's lots of areas of uncertainty, but if you go back to that single graph of reconstructing the temperature over the last century, models are remarkably good at doing it at that particular level, even if they can't do it at the regional level. So look at Edwards, also have a look therefore at Schmidt, at Gavin Schmidt's paper, JP.